Okay, so yeah, cool. So my plan is to so some of these problems are interesting, some of these problems are somewhat repetitive but instructive. So my plan is to do one interesting problem, then one random random boring problem, and flip so on. So since we talked a lot about group generators, let's try. Okay, let's try this problem. So can I actually copy this? Just a sec.
Okay.
Yeah, sorry about that. Okay, so this problem here. I mean, U and V are. I will just change it to A and B. I am audible, right?
Yeah, you're audible.
Right. So this is the information we are given, and we want to figure out what the group is. So is the question clear? You can either speak or type in the chat if it's not clear. Hello?
Yeah.
Wait, so is, is the question clear?
Yes.
Right, good. Other people? Okay, I guess it's clear. If it's not clear, I'll just ask me in the chat. I will repeat the statement and what a generator is and all that. So, ideas? So, okay, the
So
first
we have
problem
to
is,
find that, find the group.
yeah. So, let me start and you guys can help me figure out the rest of the solution. Now I can change this, right? I can write DB. I can again change this. So this is the way the problem. One of the ways to approach this problem. So can someone continue the hello? Am I even audible?
No, no, you are audible.
Cool. Okay, let me. Now AB I can replace by this. Right. Now, okay, let's try to figure out a short. We have AB equal to B square A square. So this problem is just random manipulations, nothing too conceptual. Interesting. So anyone wants to actually go through the go through all of it, or should I do it? So I'll okay. Let me do this. Next answer. Right. So I got A equal to B square. But I also know that this B square is actually equal to AB. So comparing this and this gives me B equal to 1. Now putting this and this again gives me A equal to A square implies A equal to 1, which means the group G is the trivial group 1. So this was just a messy computation. So so if even if the exact steps are not clear, the way to do it is clear, right? Do people have doubts in that? I just you just start with the A and start manipulating things. Or should I go slower? Okay. Anyway, so the reason I wanted to do this is that this presentation looks really ugly and really complicated, but after some manipulations, it turns out that this is just the trivial bit, right? Now, I guess people don't have a doubt. So, does anyone have a doubt in that? Okay, I guess no. Uh, so, one of the theorems that so can actually someone can someone actually confirm if I'm still audible?
Oh, yes, you're still audible.
Cool. So, let me motivate Lagrange. So let's say G is a group such that G has order n. Lagrange's theorem states that for all A in G, A power n is the identity. Where A power n means A star, A star, A star, A n times. So is the statement of the theorem clear? It just says that the order of any element divides the order of the group.
Shaumal just
Yeah, it's a
asked to
statement,
repeat
right?
the statement.
So if your group has order n, then the order of any element. So A is any element of G, then order of any element divides the order of the group. So this is the actual statement. I don't think we'll be using this too much. So here's the formal statement. If G is a finite group, then x power the order of G divides, sorry, x power the number of elements in G is equal to 1. So as an example, Let's take Z mod. Uh, it is it right under addition. This is the group zero. Uh, let's say that Z. But I want you to notice that for any element in Z mod is Z, A plus is that uh, is it does that answer your query? Good. So yeah, this was just an example to motivate. If you add if you add any element of Z notate Z to itself 8 times, then you get zero, no matter what your element is. That's what the Lagrange's theorem states. Now, okay, uh, an interesting problem. Yeah, we will read this like this. So let's say I have the group C6, which is under multiplication, right? Such that x power 6 is 1. Now, if I consider a map which is from C6 to C6, such that A goes to A power K, so, right. So I take every so I fix the integer K and I take every element of C6 and I raise it to that power. The question is phi bijective? So, for example, let me take take K equals to 1 goes to 1 square, x goes to x square, x square goes to x power 4. Interestingly, x cube goes to x power 6, which is the identity, and the rest of the elements, right? Is the map clear that I am squaring everything? I am squaring every element of C6. So the problem with k equal to 2 is we don't get a bijection rate. Both 1 and x cube go to 1. So if the map is clear, and okay, perhaps let me do a slightly harder question. Let's say z mod 6z to z mod 6z. Give me a map phi such that phi is a isomorphic. So what is a trivial phi that works? Yeah, a trivial phi is the identity. Send everything to itself, and that is clearly a isomorphism. Any other does any other phi work? Uh, do all of you know what isomorphism is, or should I explain that? So do all of you know what something like x plus 2, x goes to x plus 2, yeah, x goes to x plus 2, but x goes to x plus 2 is not an isomorphism, right? Because let's say 1 goes to 3 and 2 goes to 4, but 1 plus 2 does not go to 3 plus 4, right? We are working mod 6. Yeah, even x plus 2 mod 6 does not work. Right? So we want a bijection which also preserves this group operation. Right? We want so uh, x plus 3, yeah, x plus 3, x plus 3 works. And so in general, the thing is, since this is generated by only one element, if I determine phi on that one element, that determines the whole of phi, right? Because let's say I whatever I determine phi of 1 to be, 2 will go to phi of 1 plus 1, which is phi of 1 plus phi of 1, which is 2 phi of 1, and so on. 3 will go to 3 phi of 1, right? So for this case at least, determining phi of 1 determines the whole map. Now for 6, clearly phi of 1 equal to 1 works. This is the identity. Phi of 1 equal to 4. So actually phi of 1 equal to 4 does not work, right? Because x plus 3, x plus 3 does not work, right? Yeah. So 1 goes to 4, but the order of 1 is 6 and the order of 4 is 3. So x to x plus 1 does not work. Sorry, x to x plus 3 does not work. Right, so 1 added to itself 3 times, say 1 plus 1 plus 1, goes to 4 plus 4 plus 4. But this is 3 and this is 0. So 3. Right, so x to x plus 3 actually does not. So, okay, I'll just tell you. So the map which takes, can be something general about for you, x to 5x. So by 5x you mean x plus x plus x plus x plus x cubed, because we have not defined, formally we haven't defined multiplication, but yeah, x to 5x works. So x to 5x is the map which takes phi of 1 to 5. Returning to Abhay's question, x to x plus n which works. So the thing is, the maps of the form x to x plus n, even if it is an isomorphism, not all isomorphisms are of that form, because your map is like a translation, right? And translation did not necessarily respect the group operation. Uh, did you get my point? Yeah. In fact, in fact, the map should take 0 to 0. So taking 0 to any element m does not work. Right. So I hope it has been clear so far. So the general problem is, can you classify all the isomorphisms for Z mod n Z to Z mod n Z? So again, just determining phi of 1 work. So clearly phi of 1 equal to 1 works, which is the identity. What else? Any ideas? So let me repeat the question. I want to classify all isomorphisms from Z mod nz to Z mod nz.
So can you give an idea on how to proceed? Um, I don't know how to go.
So you can see that only determining the image of one determines the whole map. That part you can see.
Yeah.
Yeah, exactly. So Sudarshan gave the complete answer.
Oh yeah. Okay, got it.
So
Yeah.
another thing is one. So clearly, yeah. So a way to think about this is one has order n in this group. So phi of one must also have order n. So that is a necessary condition. But if phi of one has order n, that turns out to be also turns out to be a sufficient condition, right? Because then phi of one generates the you know range. Cool. So the answer is the all the answer is phi of one equal to a, such that a and n are co-prime. Nice. So in general, okay, let me actually do this. So in general, isomorphism from a group to itself is called a automorphism. I mean, this naming comes up everywhere, even in when you do isomorphism of trees, right?
Yeah.
Now, here is the interesting idea. So the set of all automorphisms of a group, right? The set of all automorphisms of a group is itself a group under the composition.
Hmm. And its cardinality will be the Euler-Torsson function of.
A card, no, but that is only if G is of the form Z mod and Z.
Okay, yeah, never mind. I mean, okay, yeah, for that specific example.
Yeah. In general, determining the automorphism group of a group is a hard problem. So since I mentioned trees, let me give you I won't answer the question, but I will just give you. So suppose the question is find all trees such that this has only four automorphisms, right? So one of the ways to approach this is that clearly the set of automorphisms will be a group, and there is only one group of order four. Can someone tell me what that is? Sorry, there are only two groups of order four.
One is the normal cyclic group.
Sudarshan
Um,
or Abhay?
yeah, one is the normal cyclic
Yeah.
group, and the other we can give me a second. We can just We it can sort of no, I mean I remember there being a name for that one.
Yeah, it's called the Klein four group.
Yeah, yeah, yeah.
This is this Z mod 2Z cross Z mod 2Z.
This was related to I mean, like, this not related, but one of these was related to quaternions in some way, right? Like, had the same structure.
Quaternions. Yeah, somewhat. So the interesting fact. So the standard quaternion group, which has 8 elements, which is only 8 elements, is a Hamiltonian group, which means that even though the group itself is non-abelian, all of its subgroups are abelian. Uh, yeah, all of its subgroups are abelian, and most of its subgroups look like the Klein four group. Right. Okay. So someone give me a proof that these two groups Z mod 4Z and Z mod 2Z cross Z mod 2Z are actually not isomorphic. That is to say that these two are not in fact the same group just written differently.
Wait, we need to prove that they're not isomorphism. They're not isomorphic, right?
Yeah, yeah, that is the idea. So can you actually prove that the other one is not isomorphic? Sorry, the other one is not cyclic. So quick solution case wise. So yeah, a quick solution is that Z mod 4Z has in fact two elements of order 4, while Z mod 2Z cross Z mod 2Z every element has order 2, right?
Or, or maybe are the number of subgroups different or something? I mean, we can show this in many ways, I think.
Yeah, so yeah, there are multiple ways to do this. So one of the ways is that this has elements of order 4, but this does not have elements of order 4. Because all of these elements, let's say a comma b plus a comma b is always 0 for a comma b in this group, right? Because both a and b have order 0 individually, right? Uh, was that clear? Okay, let's write down actually the two groups. And the other one I'll just call A4, since it's anyway called the client 4 group, right? Now, can I change the color? Yeah, this has order 1. Sorry, this has order 0. This has order, no, not 0, 1 only. This has order 1. This has order 4. This has order 2. This has order 4. but here everything other than this is order 2, right? Hello, am I audible?
Yeah, you're audible.
Right, so the proof is clear, right?
Yeah, it's clear.
Cool. So an interesting problem this leads to is this: z mod mz cross z mod mz is isomorphic to z mod mnz. This is given, and I want a necessary and sufficient condition on m and n. Yeah, exactly. So so can you actually construct a map from for the case when m and n are co-prime? So the answer is if and only if m and n are co-prime. Now we want to construct a map. So let's assume m and n are co-prime. Can you construct a map z mod mn mnz to 1 comma 1 goes to 1? Okay, but 1 comma 1 does not necessarily generate. I mean, that is what you have to show, right? That 1 comma 1 generates the group if and only if m and n are co-prime. So yeah, that's what we want. So the reverse direction is in fact easier. That is from z mod mnz to z mod mz cross z mod mz. So what is a very natural idea to send x to? On the left hand side, you are considering remainders modulo mn. On the right hand side, you are considering remainders modulo m and remainders modulo n. So a very natural map is this, right? And in fact, if you can prove that this map is isomorphism, the fact that this map is isomorphism is equivalent to Chinese remainder theorem. Okay, so let's try to prove that this map is isomorphism. So we want to show that this map is bijective and is a homomorphism. So clearly homomorphism is clear, right? Because phi of x plus y is equal to phi of x plus phi of y is clear, right? So clearly this is a homomorphism. We want to show that this is bijective. Any ideas? Or if you have any doubts so far.
My internet was just gone for a second. Can you just repeat what you said?
So from where you want me to repeat?
Like I understood that this equivalent to CRT after that.
Alright, so proving that this map is a isomorphism is equivalent to CRT. Now we want to show that this is an isomorphism. So we want to show that this map is a homomorphism and it is bijective. So homomorphism is clear because clearly this is true. Now we just it suffices to show that the map is bijective.
Yeah, got that. So I mean, by wait, we're not allowed. We are we allowed to assume CRT or?
I mean, you don't need CRT.
Mm,
You don't need CRT to prove this. Okay, let me push you a bit. So since since clearly I mean these two have equal order, both have order mn. To prove that the map is a bijection, it suffices to prove that the map is an injection. So let's prove that the map is an injection. We want to show this, right? Now any ideas?
This is like, I mean, this should be trivial, right? If a number has the same remainder modulo m and n, then it has the same remainder modulo mn. That is if m and n are coped, right?
Okay, but yeah, that is trivial, but you can I mean you can break that step in. Okay, let me just do this. Yeah, that is actually a part of CFT. So this means that phi of x minus y is 0, right? Because phi is an homomorphism, so you can phi of x minus phi of y is same as phi of x minus y, right? So what does this give us? This gives us that m divides x minus y and n divides x minus y, right? Cool. Any doubts, anyone? I guess not. So good. So yeah, we have shown that if this, then these two are isomorphic. Now the opposite one, which is to show that if m, n are not coprime, then ideas. Okay, let's try first. Let's prove a lemma. Order of Yeah, we are proceeding by contradiction somehow, but so okay, let's prove a lemma because one of the nice ways to prove the contradiction is using this lemma. So given z mod n z and the random element k in z mod n z, what is the order of k? That is, how many times do I need to add k to itself so that the final sum is divisible by n? This is very elementary number theory type of argument. Yeah, exactly. This is n by GCD of a comma. Yeah. Another thing, let's say order of A is equal to m and A is in a group A and order of B is equal to n, B is in the group B. So we want to know in the group A cross B, what is the order of the pair A comma B. So many ways to do this. Order of A equal to m implies, yeah, exactly, LCM of m. Cool. Now coming back to this problem. Clearly, this has an
So we
element of
show that
order.
the orders of both sides are not equal.
The order of the groups are equal, right? We have to show that the order of some element. Yeah.
Yeah, got it. Yeah.
We want to show that at no element of z mod mz cross z mod nz has order mn. If this is too easy, then I can move on
I
in
mean,
case
yeah,
this
the other
seems too
side
easy.
is, yeah, the other side, the maximum possible thing is um, LCM of m comma n. That's lesser than.
Yeah, exactly. Cool. So yeah, let me move on to more interesting problems. Wait, can I do something here? Something is there. Uh, no, cool. So this was clear, right? And let me move on to the next one. Uh, let's see. Okay, this is no, this is two number credited. Since I already did this one last time, let me try uh, this. This is nice. So problem 4. Since I hope you all have the PDF. So before actually moving on to the problem, can someone give me a, does anyone remember a combinatorial proof of Fermat's little theorem?
Um, what exactly? Oh, combinatorial. I mean, I know one that involves Burnside's lemma, but
Yeah, I think, I mean, most most combinatorial counting arguments which have a group involve Burnside lemma. So I think that that might be the proof I'm looking for. So can you recall that?
so if I recall correctly, we sort of say take a necklace with some p beads. Wait, give me a minute. I'll try to see if I can recall the proof.
Other people feel free to join in or add into his proof. Yeah, you were audible.
Okay, yeah. So
So let me help
suppose
you.
yeah,
The oh, go on.
yeah. So say we have some n colors and some p beads, then then the number of distinct arrangements, like, and say we consider rotations to be the same. I think, and reflections. Okay, I'm not sure about. Okay, so the total number of
No, you don't need reflections.
I like, what did you just say? I couldn't hear you. Hello.
Oh, you don't need to consider reflections.
Oh, okay, yeah. I was not sure about that. Um, so I think if we have say n colors, then then we can choose say the number of different, like, even say considering not rotations, the number of different things that can be chosen is n power p. So if we apply Burnside's lemma, um, I think, so say we consider the different types of movements. So one is doing nothing will have n power p symmetries. Rotating once will have n, and rotating twice will have n, and all the other, like rotating 3, 4, 5 times, all will have n symmetries and so on. So you'll have so n will be multiplied, because n for each color you'll have one symmetry, and n will be multiplied p minus 1 times, p minus 1 times, Yeah, and this should be divisible by the total number of things that we counted. That is, we counted p. So n power p plus np minus n by p is divisible by p. So yeah, that means that n power p minus n is congruent to 0 mod p. Was that correct?
Just to so a version of that, yeah, yeah, that was correct. So a version of that proof that does not use, I mean, formally does not use one-side lemma is that, so you consider all, all possible necklaces you get after coloring your all of the p bits with each of the n squares, with each of the n colors, right? And then for any two necklaces n1 n2, you consider them equivalent if they can be, if you can get n2 from n1 by rotating by a certain amount, right? Now clearly this relation is an equivalence relation. It's reflexive, symmetric, and transitive. So this divides the set of all necklaces into a bunch of equivalence classes, right? And the number of equivalence classes is the thing we want, right? Was that clear?
Yeah, that was clear so far.
Yeah. So now consider a random necklace. We want to, so consider a random necklace. Clearly, if all of the colors, clearly if all the beads have the same color, then if this equivalence class has only one element, which is itself, because no matter how you rotate, you get the same thing. Otherwise, every rotation gives you a different necklace, right? So let's let's see I let's see I be the color of the ith bead, and I have some random order of the this element, random order of the beads. So initially, suppose you had C1, C2. Initially, your necklace looks like this up to CP. Now you rotate it by X beads. You get C1 plus X, C2 plus X, up to CP plus X, and the indices are modulo X. Right. Now, if rotating by this amount, if this necklace is same as this necklace, can you prove that P must divide X? Or actually not P must divide X, but let me, yeah, I want to show that all of the CIs are equal. Is that statement clear? What I want to prove?
Yeah.
Right. So here's the idea, right? You have C1 equal to C1 plus X, but then the new necklace also you can rotate by X, and then also you must get the same thing. So C1 equal to C1 plus X equal to C1 plus 2X equal to C1 plus 3X, and so on. Now, since X and P are co-prime, this covers all the residues. So we get C1 equal to C2 equal to all of them. So this gives us CI. This gives us, to formally repeat the proof, CI is equal to CI plus X. But again, this is the same as CI plus 2X, CI plus 3X, and so on. Now, since X and P are co-prime, This indices cover everything from 1 to p. Is that proof clear? Cool. Uh, just a sec. Right. So this tells us that if all the Ci's are equal, then the equivalence class has only one element. But otherwise, the equivalence class has exactly p elements corresponding to each rotation. Right. So initially we have n power p necklaces. I remove all the ones which were singular, that is, all the colors were same. There are n of them. Now, in this set of necklaces, every equivalence class has exactly p elements. That means p must, and clearly every equivalence class has the same size. That is p, right? So p must divide n power p minus p. Is that clear? Cool. So now that we have that motivation, we kind of want to do something similar on groups. So here is the statement. Let G be a finite group of order n, and P is a prime dividing n. Right. Consider the set of P tuples x1, x2, and up to xp such that their product is 1. Right. Now we want to, the final thing we want to show is that G has an element of order P. That is, for every prime dividing the order of the group has an element of that order. Is the statement clear?
Yeah, it's clear.
Cool. So to prove this, we will try to use S. Right. That will for that will write down the definition of things. S is the set of all P tuples such that their product. Note that the order of the product matters because uh, the operation might not be commuted. Now, here's the thing I want you to show. Show that if x1, x2, xp is in S, then any cyclic shift of this, that means xi plus 1 up to xp plus I is in S for all I. Is the statement clear? Is the lemma we want to prove clear?
Yeah, that's clear.
Cool. So any ideas?
Um, just to be sure, like this comes down to saying, say, x1 is equal to xp plus 1, and so on.
Yeah, the indices are modulo p. I did not understand the question.
I mean, the lemma is somewhat trivial, right? I mean, we just multiply, say, x bar p plus, like we can do it recursively. Um, multiply the next number on both sides and show that they. I'm not sure if it's like I'm
Exactly.
doing the mistake, but
Just to, so let, let so let me do one step, and after that it will be clear. Not comma. Sorry. X1 times x2 times x3 dot times xp x1. Suppose this gives us x2 times x3 times dot xp is x1 inverse. I multiplied left side by x1 inverse. Now you multiply on the right side by x1 inverse. Sorry, by x1, right? And clearly you can do this for any. You can
yeah,
shift
got that.
however much you
Yeah,
want.
it's clear.
Cool. So here is a interesting question, which is what is the order of S? I mean, not really interesting, but somewhat interesting.
I'm guessing it's just p.
No. So order of S is the number of p tuples whose product is one. So think of it this way. Suppose you have chosen x1. How how many choices do you have for x2? Then how many choices you have for x3 and so on. So okay, let's prove this. Suppose that
Oh, like
order of the group
I
is
mean,
n.
is it like this? So we choose, for the first p minus one elements in the product, you can choose anything, but in the last one, you just choose whatever the inverse is.
Yes, exactly. So this is n power p minus 1.
Got it. Yeah.
Cool. So right. So now same as the Fermat's theorem idea, look at these as necklaces, right? And I have the same equivalence relation when two necklaces are same. When you know, that is, if rotated by a certain degree, they are the same. Then that then they are the same under our equivalence relation, right? So we have shown that given any necklace, I will be calling the p tuple a necklace for reasons. Because we have shown that given any necklace, it has, I mean, any cyclic shift of it is still a necklace which is in S, right? So clearly, right. So now this is again an equivalence relation on S. Now we look at the equivalence classes. Equivalence classes, I mean, same ideas of over. Now, can someone tell me what is the order of how many elements are there in in each equivalence class? Clearly, each equivalence class has at most p elements, right? Because I can only rotate it p times.
What do we need to find again?
So we want to find the possible sizes of the equivalence classes. So let me do some meta mathematics in the sense that, so equivalence classes means that any sense of equality
Um,
that you will
it has to be
see
either
in mathematics.
one or
Yeah,
p,
go
right?
on. Yeah, exactly. So when is it one and when is it p?
It's one if the set if n say n1 or n2 all the elements are the same, and it's p otherwise.
Exactly. So I have a total of n power p minus one elements. A equivalence class has size one. There is the number of equivalence one is g such that g power p is equal to one, right? And every other equivalence class has order p, right? So if all the elements of the tuple are equal, that means we get a element of order p. Hello, am I audible?
Yeah, 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 got that.
Right. So now suppose there are k of these, k equivalence classes of all length p, and l of these. Then we have n power p minus 1 is equal to p times k plus 1 times l, right? I'm just counting all the elements of S. Cool. So now can you, so see, the thing we want to prove is that this set, I mean, clearly this set has g equal to 1 in it. We want to show that this set has something other than g equal to 1 also. That is, there is an element which has order exactly p. So we want to show that L is greater than 1, right? We have n power p minus 1 is equal to p times k plus L. And to show L is greater than 1. And we already know that L is at least 1. So I think this will be the last problem of this session. There is one thing in the problem statement which we have not used yet. Exactly one thing. We have, uh, yeah, we have used the fact that G has order n. We have used the definition of S. But so what is the information that we haven't used?
That P specifically divides in.
Yeah, exactly. So we somehow need to use that to show that. I mean, now can you show that L is greater than 1? So P divides this, P
So
divides
if we
this.
take mod P,
So we have P divides L. Yeah, go on.
yeah. So if we take mod P, then P divides L, and P can't divide something that's one mod N.
So we know that L is not 0.
E- Yeah,
So L is at least P.
yeah.
I mean, clearly L is not negative or anything.
I mean, P can't divide one, so
And
L
we are
can't be.
done.
Yeah, yeah, nice. Yeah, that's really nice.
Right. So we have actually proved something really strong. We have proved that no, if we have a finite group, no matter what group it may be abelian, it may be non-abelian, it can be the worst possible group, but whatever prime divides its order, it has a element of that prime order, which is very, which is a very strong statement. And so the formal name of this theorem is Cauchy's theorem. And right, so I don't have more time left, so I will just give a quick exercise. But this exercise will need uh, will need the notion of the normal subgroup. So if you know what a normal subgroup is, you can try this exercise. We want to prove that suppose G is abelian and G has order n. We already know that for any prime P dividing n, G has an element such that the order of that element is P. Show that for any D dividing n, for any divisor of n, G has an element such that the order of the element is D. So this is an exercise, and this will probably need the notion of a normal subgroup. But yeah, so this tells us that finite abelian groups are relative. I mean, much nicer than general groups. You have for every for every number dividing the order, you have an element of that order. And yeah, that's it. That's all I have for today.
Thanks a lot for that.